Okay, well, let's get started on our exercises. So, way we would like to do this is we're going to start with examples of accessing uh, observed seismological data, and I'm going to ask Fabio to uh, share his screen and um, show us the kind of exercise description. We've identified a particular uh, target task, description of some data. We're going to describe how to retrieve and access. S- so someone or Fabio, can you share your screen? And
I can, and the link to that will be posted on the chat, right?
yes,
Okay, let me share my screen.
so could someone, either Scott or Akash, could you post that link to this PDF? So we're going to show a PDF that has various links in it, and we would like participants to follow those links and to work these exercise together with us as we go through this. So okay, so we've identified a theme for this exercise that was contributed by Ahmed Elbana, who described seismology as data-driven and model-guided, which I think is a good description of how seismology research is performed. So the basic approach is we're going to introduce a four-step process for working with seismological data. And the idea is that basically you go through these four steps when working with nearly all open seismological data. And we'll show examples of following these four steps as we work with each of the four different types we're going to present in our exercises today. So the steps are locate the data, select the specific data you want, download it, and use it. So the connection between this activity and the applications that you'll see later in the workshop and the next days is that both observational, that these simulation codes that will be discussed later will often make use of open seismological data. So it's likely that this will be helpful, or be accessing these type of data sets will be useful when you use those research applications that will be presented later in the week. So seismology is a data rich research field. We have many type of observational instruments like seismometers, strain meters, GNS stations. However, there are many aspects of the Earth and many earthquake processes which are difficult to observe directly. Such as, what is the Earth's composition at depth? What is the location and the structure of faults? We don't have good, clear observations of those. So to address that, the research community often develops models, which are simplified representation of how the Earth works. These help us study aspects of earthquakes that are difficult to observe. And so computational models often suggest types of behaviors that can be observed. So together, model and data help us develop a better understanding. So as we've said, the kind of learning objective is to retrieve this first exercise will be two types of observed data, including ground motion waveforms and earthquake catalogs. And then the next exercise will do two types of seismological model data, fault geometry and seismic velocity model. So at this point, for this, you only need a web browser. So why don't we go to exercise one, access to ground motion observations. So in this exercise, we're going to go through the 4-step process: locating, selecting, downloading, and using. So at the end, you'll have a better idea where to find observed data, how to specify the seismogram you want, and how to download it onto your computer. We've identified a specific goal for the exercise to help us work through the process. So the goal we defined for this is we're asking participants to download a seismogram as recorded by the University of Southern California Broadband Station. Its ID is called USC. And we want the seismogram that shows velocity ground motions at USC during the ridge crest magnitude 7.1 main shock that occurred in July 2019. So that's the goal for this exercise. We tried to color code. There are links here with background information, but the ones in green are where participants might want to type or follow along as we go through this exercise. So let's start with step A. Locate. Where do you get observed seismograms? Well, due to open science practices, there is a wide range and a number of different places you can get observed seismograms, and they come in different forms and types. So I mentioned previously there are real-time streaming seismograms. You can go to the USGS or Sage Gauge streaming seismograms. If you click on those links, it'll take you and show you. You can see kind of real-time streaming data. There's also strong motion data. So strong motion data is particularly of interest to engineers. So there's a engineering organization that's collected basically strong motion data, and that you can find at the Center for Engineering Strong Motion. There's also collections of event-oriented seismograms. So after an earthquake, research organizations will often collect, here are all the observations, all the ground motion observations we have for this specific event. And so there's a link there where you can give a list of earthquakes, and basically on it with a simple click, you can download a whole collection of earthquakes related to a specific earthquake. And another source of observation is continuous data sets. So some stations, typically high quality stations, are recorded continuously, whether earthquakes are happening or not. And these data are available through EarthScope, and you can request data through these services for arbitrary time because it's considered continuous. So, let's starting with step A in our process. Where can we get? We've got a goal to get the USC data for the Ridgecrest main shock at USC. So for that purpose, I'm pointing and recommending the Sage Seismogram Data Access URL Builder. And so if we click that link, it leads us to this page and web form that asks us for a variety of information about which particular observed seismogram we want to get access to. So this tells us what information we need to collect to prepare our data request. So if we go back to, now we're into step B. How do we specify the data that we want for this particular station and earthquake? So the standard method, and when we look at the form, it's asking us to identify our station and the information we want in what's called seed format. The seed standard provides a standard way to identify seismic networks and stations. There are links here on this page that identify the seed naming conventions. There's also links here to a list of ANSS stations. This is the Advanced National Seismic System. And there's a list of Southern California seismic stations. So somewhere in those links, we should be able to find the information to specify the USC station that we're after. The way we need to specify it is going to include at least these four kind of fields: a network ID for Southern California, operated by Caltech and USGS. The network code is CI. For the Northern California seismic net, operated by Berkeley and USGS, is NC. Stations are given a unique 3 or 4 letter character, USC's USC. There's a location ID that's was introduced more recently. It's a way to identify if you've got multiple instruments at the same location, possibly at the surface and at depth. Location code will help you specify which of the different instruments you actually want the data from. And then the channel type identifies the type of instrument. Is it broadband? Is it velocity? And also the sample rate. And really, it's useful to look at the seed channel naming conventions to help identify exactly which channel you're interested in. So, but kind of key distinction is the usually ground motion instruments. There's different types. Some instruments are very good at recording weak ground motions, such as distant earthquakes. These are often called broadband stations. But one of the issues with these is they can often exceed, during a significant earthquake, they can often exceed their maximum ground motion levels. So it's difficult to tell what the peak ground motions occurred. So there's another category of instruments, often accelerometers, which are good at recording strong motions. So, however, these instruments won't record ground motions unless they are from large nearby earthquakes. There's also issue about what sample rate the data. So there's a wide range of samples. Basically, the sample rate to retrieve or to access depends on the type of your research. The higher frequency that you're studying, the higher sample rate data that you'll want to retrieve. High sample rate data can get very large, so you try to find a right balance where it's high enough, but not the sample rate you work with is high enough to include the frequencies you're interested in, but not too high to use all your disk storage. Okay, other fields that need to be entered or into the form we looked at is the component, the orientation code. We're going to look for the vertical component. So typically instruments are aligned north, south, east, west, and vertical. Some instruments, for example, may record only vertical motions. It's kind of instrument dependent what components are available. There may also be a quality code associated with data. We're going to look for the best. That might be which implies it might have been reviewed or corrected as needed. Okay, so all of these are helping us collect the information that we're going to enter into the form. We also need the start time of the seismogram that we want expressed in UTC. The point of confusion here is that sometimes earthquakes are expressed in local time, but when you retrieve a seismogram, you need to specify it in UTC time. So then the duration is how much of a seismogram you want. I think our goal here was 5 minutes or of data. So having looked at all those fields, now we're kind of collecting the information we want. Here to get the origin time, the start time, we can go to the USGS website about the Ridgecrest main shock, and it will give us, it'll tell us the origin time for that event. we're going to retrieve USC broadband 40 sample per second vertical component. So when we collect all the information required by the URL builder, we were going to enter one additional field is what format we want to download the data in. So for this exercise, we're going to work with CSV format because this is a simple ASCII format. As may be more common to use other formats such as SEED, but for simple purposes, a GOSV is a good choice. So at this point, we've collected all the information we need to enter in this field. And so if Fabio, maybe we can go to the other screen and you can enter that in. And so please feel free to work along with us as we do this. So network code, the station, USC. So this start time is the origin of the earthquake, and end time's 5 minutes later. So the channel is BHZ, so that's the 40 sample per second broadband. We're going to specify the best quality. We're going to specify the Geo CSV format, and the other fields are optional. And if we look at the lower part of this page now, here in this yellow box that Fabio is showing, basically what this website has done is generated a URL. So it's a uh, interface or a way to query uh, this data set that includes the information that we just provided. And so now if we click that link, what we expect is that our system will download a file that contains the seismogram that we're interested in. So I think I saw Fabio's web browser kind of indicate that a file had been downloaded. If we scroll down a little bit on this page, oh, I'm sorry, back to the exercise. So we move to step C. We've clicked the URL at the bottom of the page, and what we expect is that it will download onto Fabio or your computer a file with this type of label. There's a time on here. That's time, I believe, is the time you issued the request. It's not the time related to the data or the seismogram that requested. But we see it's a CSV file, and that allows us to open it with a simple text file. So just comment here, typical things you might want to do with a seismogram. You can look at it, you can use it, identify phase arrivals, calculate peak ground motions with it. If you open the file, it's going to have time and some samples in it. But a quick way to look and say, does this look like a seismogram? When we prepared this, we opened it with Excel and did a plot. And basically, we can just a simple plot. We don't have, it's not well labeled, but we can see there's a period of time where there's no motion at this station. And so that would be the wave propagation time between the earthquake and USC. And then for the E first arrival, and then significant ground motions and potential S arrival later. So even this very simple plot, this looks like a signal, earthquake ground motions at USC. So that's indication that we retrieved the seismogram that we're interested in. So okay, so I hope as participants you'll give this a try and try it and see if you can download it onto your own computer and open and verify that you've got a seismogram. Why don't we scroll down a little bit, Fabio, and just talk about some issues related to working with observed seismogram. So one of the key issues is how to properly interpret this. Basically, you get a timestamp and a number, um, and it's important to try to understand and then properly interpret what that number is. So the different possibilities. And basically, the question is, what are the units of that number? So are these values in counts? Are they acceleration? Are they velocity? Are they displacement? So uh, that's important, and it should be provided in the metadata somewhere. Um, in this case, the metadata indicates that the headers listed is meters per second, and it provides a scale factor. So to convert the numbers you find in the seismogram into meters per second, you need to do a adjustment. So for example, this first sample, minus 12, 173, is units are at this point are not in meters per second, but there's information here in the metadata that allows you to convert to that. Okay, well, we're almost through here on this kind of initial exercise or retrieval activity. Of additional comments are, this is a simple way to retrieve a seismogram for an event, but it would be tedious to do this for a large number of seismograms. So um, if you want to work with a large number of seismograms, there are other ways to retrieve them, including programmatic access that will allow you to write scripts, so you could retrieve a large number of seismograms more easily. In addition, it's worth knowing, once you get the seismogram onto your own computer, you'll probably use other processing software. It's not common to use Excel, for example, for research purposes, but there are specialized codes that are well suited to working with seismograms. A couple of them are mentioned here. A seismic analyst code called SCEC and OBSPI are both kind of widely used codes for working with seismograms. Okay, so that's the first exercise. How are we on time? I think we've got one more exercise of this session.
You have about 20 minutes, Phil.
Okay, so I think that and I have not I haven't been monitoring the chat. Anything we should address before we move on to the earthquake catalogs?
I don't see any unanswered questions at this time.
Okay. Okay. So we're going to work one more example, this time earthquake catalogs, and then that'll lead us up to a break here at 10:30. So let's move on to exercise 2, which is how to access earthquake catalogs. And we're going to go through our similar 4-step process. So if we go through this, you should be able to find observed catalogs and specify the catalog you're interested in and download it and be able to use it. So we've identified a particular goal for this activity, which we defined as download an earthquake catalog that has a list of all the earthquakes that occurred in the lower 48 states of the US, called the conterminous US, that are magnitude 4 and larger, uh, starting 1 minute before the ridge crest main shock and continuing for 1 week after the main shock. So the general idea here is when there's a large earthquake, we anticipate a significant number of aftershocks. So I'm going to assume, we're kind of assuming here that most of the magnitude 4 earthquakes that happened after ridge crests are probably ridge crest aftershocks. So, how many do we expect in the first week after a 7.1? So we can go through this exercise, retrieve a catalog of all the earthquakes, magnitude 4 and larger, and that'll give us an idea how many magnitude 4.5 and larger events that happen in the first week. All right.
So we have a question in the chat
Yeah.
by Dewan. If we multiply counts by scale factor, are we going to have information about displacement or velocity?
Of velocity. That's in units meters per second. It's an important issues of, even if they say velocity, we have to know, is it meters per second or centimeters? And it definitely can cause confusion if we don't specify the units properly. Okay, so that's a good question. So why don't we go on here to trying this exercise of downloading earthquake catalogs. Okay, so just a little bit of background on earthquake catalogs. For research organizations that operate seismic networks, one of the key data products that they need to produce is a earthquake catalog. And so this lists essentially all the earthquakes that have been recorded by their network. For each earthquake, typically what you'd find in the catalog is an origin time, a location that includes latitude, longitude, and depth, and a magnitude for each earthquake. A catalog doesn't necessarily have to contain all of this information for every earthquake, but that's typically what we would expect. If you run a seismic network, you can increase the number of earthquakes you detect by adding sensors or improving your processing methods. So often networks are evaluated by what their catalogs, how complete their catalogs are. Do they detect earthquakes down to what magnitude? So in Southern California, it's got good station coverage, a lot of stations and good station coverage. The catalogs are considered complete. Probably we can be fairly sure every magnitude 2.5 and larger will be found in the catalog. But if you're operating a seismic network in a less populated region or somewhere there's fewer instruments, your catalog may only include earthquakes down to magnitude 4. So you're only kind of listing large events. But for Southern California, the catalogs are very complete. In the US, the USGS provides the COMCAT catalog. It's authoritative. Basically, there are a lot of earthquake or seismic networks. They contribute their catalogs to USGS, and USGS kind of sorts through them and redistributes the information, and they kind of identify what they consider the most accurate or most reliable earthquake information, locations, and magnitudes. It's worth knowing that in the recent years, a wide variety of what might be called specialized earthquake catalogs are being developed and are available. As one example, there are earthquake catalogs that identify very small earthquakes. These catalogs may be generated using machine learning methods, and they will list, 2 or 3 times the number of catalogs found, for example, in Comcat. But the great majority of the earthquakes are very small, and so they're kind of specialized use. So we're in our kind of stage of here finding a catalog. Where do we go if we want to retrieve information earthquake catalog? So there's an example here. If you go to the USGS provides an inventory of earthquake catalogs. If you click on that, Fabio, you'll see kind of illustrate the point that there's kind of a wide range. These are all seismic networks. All of them generate earthquake catalogs of one sort or another and contribute them to USGS. There's one there, CI, that's the Southern California one, and that's the catalog or the in Southern California. Okay, thanks. Why don't we go back to the presentation material? Okay, so that is a collection of where you might find earthquake catalogs, but for us, we're going to use the Comcat search page. And so that's step A1. If we go to the this URL, it brings up this earthquake search web form to help us search earthquake catalogs. And this helps list the information that we need to provide as we to retrieve the catalog that we're interested in. So let's, after looking at this, now we're going to collect the information we need to fill out this form. So here we're in step B, we're specifying the earthquake that we want in our catalog. So we need to identify the region, start date and time, end date and time, minimum magnitude, maximum magnitude. We can start by getting again, information about the Ridgecrest main shock. I would rely on the USGS webpage for information about that. We've looked at the form, and if we scroll down a bit here, Fabio, we can look at here, step B1. We see that the form is asking us for these particular fields. The magnitude we're going to select is 4.5 and larger. We're going to have a custom date time, which will be 1 minute before the Ridgecrest main shock and the end time of 1 week later. A region, conterminous US, a minimum magnitude, we can leave the max magnitude blank. And we're also going to specify output format. So there's a variety, the catalogs can be distributed in a variety of format. We're going to use the GeoJSON output format. So if we go back to the web page and enter that information, so again, I encourage you to try this yourself. When we developed this exercise, we decided to start 1 minute before the main shock, just to see if maybe there were some foreshocks. I don't think we discovered any, but it's a possibility. We selected the magnitude 4. We've identified the date and time. We've selected geographic region. We're going to go to the output options now and select the GeoJSON. And at that point, we've specified basically the catalog that we're interested in. And if we click this search button here, so it looks like in this browser, it displays the file that it retrieved. I've found that this is browser dependent. I think Firefox downloads the file and maybe Google Chrome displays it. But if we go back to the exercise, page, we scroll down. This step B2 shows the fields that we've specified, and we've it looks like, Fabio, when we set this up originally, we set a GeoJSON, we said a CSV file. Maybe we could change that output format, and maybe in that case it'll download the file.
Yeah, I got a file now. Let's see.
Okay. All right, so let's go back to the exercises and we can show basically what we expect to see in that file. Okay, so we were on step C. Oops, sorry, can you scroll back for a moment? So step C, we said we want to download it in CSV, which stands for comma separated values. And we expect you would get a query.csv file. And now you can open that file and see the list of earthquakes. So if you open it with a text file or with a, I think I opened this with Excel. You can open it with a text editor, but open it with Excel. And at this point, we kind of get an answer to the question, how many catalogs or how many magnitude 4s occurred in the first week after Ridgecrest, and it looks like 27. So like 4 a day. So I don't think it's evenly distributed, but yeah, the first one, the bottom of the list here was the magnitude 7.1, and I see the largest aftershock is like there. Oh, there's a 5.4. There's several fives in there as well. So anyway, it just gives you an idea when there's a large earthquake, it's not an isolated event. There's a large earthquake brings along some of its friends. So why don't we go back? Yeah. So why don't we go back to the presentation? I just have a few additional comments here about working with catalogs, and then we'll be ready for our break here. So next steps. All right, so I want to make a note. Earthquake catalogs, including this one, this Comcat, are dynamic. So information in catalogs can be updated. New information comes in, earthquakes get relocated, magnitudes get adjusted. So if you retrieve an earthquake catalog today and you retrieve, you specify exactly the same time period a week from now, it's possible that you'll get a different set of earthquakes. So that actually presents challenges working with earthquake catalogs because they change, but basically the expectation is they continue to improve. So the most recent version is the best available catalog.
5 more minutes, Phil.
Okay, thanks, Scott. The other important things as we noted with the seismograms, doing a web-based catalog search like we just did could be tedious if you're going after a lot of catalogs. And so the Comcat provides APIs so you can write scripts that will automate your catalog retrievals. And it's also worth knowing that catalogs, that there are several seismological software that provide access to earthquake catalogs. So including PyCCEP and OBSPy both have interfaces that allow you to retrieve earthquake catalogs. And using these tools rather than the URL browser have certain advantages, including the ability to plot the catalog on a map, showing the spatial distributions, showing the time distribution and magnitudes, and multiple other plots. So if you get far in and start working with earthquake catalogs routinely, you'll probably be drawn to using these specialized catalog processing codes. Okay, so I think that's the end of this exercise. Got 4 minutes here, and if there are any comments or questions, and then we'll take a brief break and move on to our next presentation topic. Okay, well, I'm not hearing any questions. So we hope you'll explore and try out some of these tools. You certainly could pick different earthquake and location, and try to retrieve an observed seismogram for another event, or potentially do something like we retrieved the ground motion that USC has recorded on the broadband instrument. I believe there's a co-located accelerometer, so a strong motion instrument. You could retrieve the same kind of time frame and see if the ground motions are well recorded on the strong motion instrument at USC for that event. You could pick another earthquake cataloger and retrieve that, um, based on these exercise, develop some variation of interest to you. So I think with that, we'll pause for a moment. We'll go for a brief break and reconvene. I think we're next scheduled is 10:35. Does that sound right, Scott?